In this module, we're going to be going over how to work with linked data with graphs, primarily with the NetworkX library. So for our visualizations, we'll want to make sure that we have the matplotlib inline set for the notebook. And we're going to do a little diversion first, and that for the in-class exercises, we'll do some work with email. So I'm going to demonstrate getting data out of an inbox. So in this case, we're going to use a couple of libraries. We're going to use the IMAPLib. We're going to use the getPass module, and this prompts for a password without echoing it back to the screen. If you're using an IPython version older than 3, the getPass will bring up the prompt in the shell that you launched the notebook from. In the newer version of the IPython notebook, the getPass will work within the screen, within the notebook. Okay, so getPass, this will assign, without echoing back to the user, a password variable. And then we can use that in accessing the logging into the email server. So this is the information for logging into the University of Utah. And I did have this that I was pulling all the messages. My inbox is way too large, and it kind of just choked after about 3,700 messages. And so I'm saving those, and then we'll be able to access those later. Okay, given that I have those messages, Python has tools to parse the messages and break it into different parts. And so we use the email message library. And so there's a parser, a built-in email parser. And so here I am going to be writing out the to and from aspects of the from and to aspects of the message as I sort through those. Okay, so let's get into graphs. Graphs are a data representation consisting of nodes and edges. So nodes are entities. They're the concepts. They're the nouns of the data that we're modeling or working with, and edges are relationships between those nouns. And so a couple of examples. So in text, nodes might be the words in the sentence, and edges are the relationships between the words. Like this adjective modifies this noun. This adverb is a concept, and the edge pointing to a verb is that relationship would be modeled with an edge. It's analogous to anatomy. So I've used graphs to just represent different anatomical features, and the nodes are the anatomical piece, and the edges are adjacency. That this organ is adjacent to that organ. So the primary package for working with graphs of this nature is called NetworkX. It was developed by Los Alamos National Laboratory, and there are a variety of different kinds of graphs. So that we have undirectional graphs, we have directional graphs, we have multi-graphs, and so the details of all these different types of graphs are provided in their very nice documentation. Some things to highlight: that graphs, nodes, and edges can all have attributes, and the attributes are stored as a dictionary. So each node has a label, and each node also has a dictionary, possibly empty of attributes. And this is the same for an edge. Each edge also has a label. Its label are the labels of the beginning and ending nodes that define the edge. And as with the node, each edge also has a dictionary, possibly empty of attributes. And just the top level graph can also have a dictionary of attributes. Here are some links to some various NetworkX IPython notebook tutorials that I found that you should work through. I didn't double check this, whether NetworkX might be already part of Anaconda, in which case you'd want to try to install it with conda install NetworkX first before using pip, but it can be installed with pip. So a very natural type of data for graph representation are ontologies, like the OBO format that you're working through with the homework right now. And so here's an excerpt from a OBO ontology, and we're going to read it into a NetworkX graph. And here's the code for that parser. And you can see what we're going to do is we're going to have each concept that we read in be added as a node. And if that, what we read in has defined ISA relationships, then we are going to, for each ISA relationship, that we're going to add an edge between the current node that we just added and the concept or node listed in the ISA relationships. And after we parse this, we have a graph that has 80,938 OBO terms, or now nodes, in the graph. I just wanted to highlight that one of the advantages of this representation over what you're doing in the homework. In the homework, you have a one-directional relationship that you have a label of this concept is so it points up to the parent. But from the parent, you can't go down to the children. And in the graph representation, both the parent and the children relationships are easily explored. So we have 6,910 edges. Those are the relationships between concepts, and just under 9,000 concepts. And here, just showing pulling out ontology nodes data equals true, and I'm pulling out the first 15. So this is the concept, and so this is the node, and then this dictionary is the attributes that are associated with that node. I can pull off the nodes. See if I, without the data equals true, it defaults to data equals false, and it just returns the nodes for me. Similarly, there's an edges function that returns a list of edges, and we can also pull off those, but we did not assign any attributes to the edges. Okay, so here in more detail, here's a single node where we have our concept. So this is our disease ontology identifier, and then these are the attributes. And you can see that the ISA relationships are not explicitly instantiated here as attributes of the node. Rather, they are going to be the attributes. They're going to be represented through the edges that are coming out of the node. Okay, so here I'm kind of going to write some just functions to make querying the graph maybe a little more user-friendly for us. So I'm going to define a function that has node with attribute, where attribute's going to be a a pair of what the attribute is and what value that I'm interested in. Probably not the most user-friendly user interface for this. But I'm going to loop through the nodes of the graph, and I'm going to try to get the attribute that's keyed with the value stored in attribute 0 and ask whether it's equal to attribute 1. And I'll have a little illustration of this in a second. So here I'm going to write a function that's going to return an attribute of the node. In this case, I'm going to pass in the graph and the node that I'm interested in, and then what feature I want to pull off. In this case, it's going to default to returning a feature of name. If it doesn't have that feature, then it will return a none. Should probably make this, oops, a key error, just to be more specific. Okay, so this is a very, all the graph, and what I'm probably interested in are pieces of the graph. So we're going to look at how can we extract useful subgraphs. So what I'm going to do is I'm going to get the path of a subgraph where I can pass in a target, like a high-level parent, then some concept in the graph, and I'm going to return the path, if it exists, that connects the root from the target. So in this case, I'm going to use the Dijkstra path. And so the Dijkstra is a famous shortest path algorithm that was published in the 50s to extract the path from root to target. And then given those nodes that constitute that path, I'm going to pull them off and put them into a subgraph and return them. So let's look at some of this. So my hat has nodes with attributes, so I'm passing in the ontology graph, and I'm going to ask, is there any node that has the attribute name equal to sarcoma? And it does. It's a node with the label DOID 1115. Here is a attribute of the ontology.graph accesses the graph, and I'm asking if it has an attribute roots, which it does. Well, there's one root, and that's what the DOID concept for. Okay, here's demonstrating the Dijkstra path that we are going to be using in our function. So I'm passing it the root of the graph and then a concept, the sarcoma graph, or whichever concept that was. And this returns the list of nodes. That's the shortest way to traverse the graph from the root down to the concept I was asking about. And you see there's 3 intermediate nodes. And here we're pulling out the subgraph, and we're plotting it. And the draw is just using matplotlib, and the draw is just kind of a top-level default drawing function. There are you have much more control if you want to take it. You can specify. You can draw the nodes, edges, and labels all separately, so you can customize them how you want. So here I'm getting a descending graph, so I'm going to pass in some parent node, and I'm going to use the descendants method of NetworkX to get a list of all the nodes that are descendants of that root, and then I'm going to use the list of nodes to select a subgraph and return that. And so here we're going to get a cancer subgraph of all the descendants of sarcoma. And here's our graph with the labels, but those labels aren't particularly meaningful for us. And so we'll want to explore if there's ways we can make these drawings more useful. And so I'm going to define this function draw oboe graph, where instead of using as the label, I'm going to pull off the name and label the graph with the name. And so here I'm going to identify, I'm going to get my list of nodes, and then I'm going to separately draw the network X edges, nodes, and labels. And I'm using a GraphViz layout. I'll go over this in a second. This requires additional software to be installed, but there are other layouts that you can use. So the position keyword takes a layout. In this case, I'm using the GraphViz layout and using the dot program to define where the nodes should be placed. And the network labels takes as the labels need to be in a dictionary, and so here I'm keying it by the node, and then the value is going to be the name, the feature that I pulled out. In this case, the defaults with name. Oops. Oh, that should be drawn. Here we are. Oop. So here you see we got disease. So a sarcoma is a cell type, cancer is a cancer, is a disease of cellular proliferation, which is a disease. I can resize that a little bit for you. Okay, so this is going to be a function that's going to give us a named traverse. So we get a Dijkstra path, but instead of just printing off the IDs, it's going to print off the name instead of the identifier, the concept. So as we run through this, scroll down here. Oops. Did I not execute this? Okay, so that's just the function call. This is going to return the first root of a graph. That's like the top level node, and you can have multiple top level nodes. So I'm returning the first one. And so here I am printing off the named traverse from the top level node, which I got from the get graph root, to the attribute that I want to see. So this is printing off the names of the traversed path. Okay, so here's a function to find the lowest common ancestor. And so what we're going to do is we're going to trace off the path from the root of the graph to each one of these nodes and then find the intersection path of them. And I'm going to see if there's a squamous cell carcinoma. So there is. And I'm going to find what the lowest common ancestor is for a sarcoma and a hepatocellular carcinoma, which is a liver cancer. And a sarcoma is a connective tissue malignancy, and the lowest common ancestor is just cancer. Here I'm pulling off the nodes with attributes. And here the lowest common ancestor of squamous cell carcinoma and melanoma is cancer. And here printing off relationships around melanoma. And when I create a subgraph, it doesn't automatically copy the attributes. So here I'm creating a function to copy the attributes when the graph is generated. And here's, again, a melanoma tree. Okay, so these graphs are fine, but I wouldn't really consider them publication quality. And so there are some other packages we can use, and we're going to look at specifically using GraphViz to create the plots. So my apologies to Windows users in that this can be very difficult to install for anyone. And we did have some people last year that on Windows were able to install it. On my Mac, I had to do several of the following things. I had to install GraphViz with Homebrew. Then I had to install PyGraphViz, and then I had to install PyDot2, which is an override of the PyDot package, which doesn't work with the newer version of NetworkX. Anyway, it was kind of convoluted and confusing. I think when people were installing GraphViz on Windows, there were issues about whether they were installing 32-bit or 64-bit. But it is doable. It may not be doable during class. So having installed all that, I want to reload my NetworkX to make sure that my functions are available. And here I am going to create a drawing using the PyDot function, the toPyDot of NetworkX. And I'm going to generate these PNGs or PDFs. And so here I've got a nice layout of a disease of cellular proliferation down to a sarcoma. And similarly here, getting a fallopian tube adenosarcoma. They're not all linear paths. PyDot's going to work on what it believes is the best layout for the data that you have. So here are the children of a melanoma. And you can write out the entire ontology. So let me see if I can open that. So it becomes this huge graph, which we have to really zoom in. So it doesn't really have any functional usefulness other than if you had a giant printer and wanted to make some wallpaper. Okay. So here's printing off the names of the graph with vertical bars as a delimiter. And then here's just an example of using graphs for a different purpose with NetworkX. And so this is Donald Knuth is a famous emeritus computer scientist at Stanford. And so we have this data set of cities and the miles between them. So it stores the city location and the population of each city as attributes of the graph. So this is just pulled off from the NetworkX site, and with little modifications. So we're going to open the file to read. Use the gzip file. We're going to read lines. We're going to parse it out. If we get down here, we are going to add a node with cities. We're going to add to it as an attribute the position of the city, and this is, and then the population of the city. Okay, and then we're going to graph it. And so we're going to read it in, iterate over the edges. So this is the beginning, the ending, and the attributes of the edge. And let's see if we add edge. Let's just come back up here. This is an example of an attribute an edge having an attribute. In this case, it's we're going to call it weight, and it'll be the distance between cities. Okay. And so, okay, let's look at our draw function. So we're going to use as the position the position that was attached to each of the nodes, the location of the city. We're going to draw how big the node is based on what its population is. And we're going to alternate color. And in this case with labels, it's going to be false. And we can draw that out. So here is the resulting graph of the United States. And in class, we can look at playing around with different things like drawing the city names on the graph. Okay, the next section of the notebook, we're gonna work on exploring the mailboxes in class